Good morning. Today I'm going to give you a wee brief re-explanation regarding floating point representation. Some people have been doing really well with the work that has been assigned, and one or two people are having a little bit of bother with it. So hopefully this will help with the practical work that has been assigned. So first off, we're going to talk about using binary to represent real numbers. Previously, in the last lesson, we were looking at using binary to represent whole numbers, converting positive values between 0 and 255 using 8-bit binary. So, when we're talking about real numbers, we're talking about values that have decimals in them. In other subjects like physics, maths, you may have used scientific notation. When we're using scientific notation, it's essentially a way of writing very, very large or very, very small numbers in a much more manageable, much more efficient method. When we do this in computing, because computers can handle amazingly large calculations much better than we can, we use a similar system. Instead, we call it floating point representation. So, just to give you a wee reminder to cover scientific notation, if we have a wee look at this number here, you can see we have 545 million, which is obviously a very, very large number. To make that a little bit more easy and a little bit more noticeable, what we have is, you can see here, it is displayed as a decimal number 4.45 times 10 to the power of 8. What that essentially means is we have the value of 545 times 10 to the 8. Now, as you can see, apologies for my terrible handwriting, what this means, this little value here, the power, or in computing we refer to that as the exponent, what that tells us is the decimal place has moved 8 positions. So if we have a wee look, I'll write it out again in a different colour so we can see the extended value. So if we have a look, we've got 5, 4, 5, 0, 0, 0, 0. So originally our decimal place is here, but invisible. So what we've done is we've put that in, and to make this manageable, we'll count 1, 2, 3, 4, 5, 6, 7, 8. What we want to do is we want to end up with one single value before the decimal point. Oh, apologies. Just pop that. Oh, we'll just pop that in there. So then we can get rid of all these zeros, and that leaves us with our value here, 5.45 times 10 to the 8. Simply meaning that we've moved the decimal point 8 places, and it makes it much more efficient to write. So a little bit more about the mantissa and the exponent. When we're storing small numbers or very large numbers, we essentially actually break it down into two values. You can see down here I've got 5.45 times 10 to the 8. What we can do is the exponent is essentially the power, this value here, and our mantissa is the decimal containing value at the front. So if we were just looking at this value here and I asked somebody what was the exponent, you can see this is the power, and straight away we would just say the exponent is 8, and our mantissa is simply this value exactly as it is there. Now, although we're reading this in denary form, so in our number system, normally the computer would handle this in binary. Just be aware, at National 4 and National 5, you are not required to know how to change this into binary. So if you're worrying about, oh, how do I get that into binary form? It's not something we need to concern ourselves with at the moment. You may have to give the exponent in binary, but that will always be a whole number and it will be handled in exactly the same way we were doing before. You can see up here I put a wee bit more information. The exponent, that tells us how many places the decimal point has been moved. The more binary bits that we have assigned to this, the more numbers we can store, so it gives us a bigger range. Similarly, this decimal place, the more values after the decimal point we've assigned to it to store, the more accurate the number would be. If we assigned it only 2 values here, obviously there would be some rounding, so it wouldn't quite be as accurate as storing the whole number as was. So if we have a look, we'll talk about very small numbers now. So if I ask somebody to do the value 0.000926 using floating point representation, first off, the easiest step we would need to do is to write it out just as a whole number. Now we want this, so we have this number 9 as our first value before the decimal point. So we need to count, and we'll just jump this along. So 1, 2, 3, and that's where we would want it. We want it in here, so we've counted and we've moved that 4 places. Unlike in the previous one, because it's a very small number, we've moved it to the right. So the exponent will be 4 as we've got it, but because it's going to the right, we need the negative 4. As you can see, I'll pop that there. Now the mantissa, given that we've moved our decimal point here, we basically just pull this little bit of information down and pop it over on the left hand side before the multiplication. So the mantissa in this case would be 9.26. As I've mentioned, at National 4 and National 5, you do not need to be able to know how to convert from decimal numbers to binary with real numbers. We will do, as we've covered, we do whole numbers, but we don't need to worry too much at the moment about real decimal numbers. You will be required to state the mantissa and exponent if you've been given a value. It might already be in floating point representation form, or it might be in a larger form that you will need to convert. And then lastly, as I've mentioned, the mantissa and the exponent, the number of bits allocated to these values to store them, has an effect on the range and accuracy. So the mantissa and the exponent both have an effect on the range and the accuracy, and you may be required to state what the effect actually is. Hopefully that's helped with some examples. So to give you a little summary of the key points for floating point representation, I will now just go through some. So as we've covered, all real numbers can be represented using floating point representation. By real numbers, we again are referring to any number that is a decimal number. In floating point, all numbers are broken up into 3 sections: the mantissa, the base, and the exponent. So any number that is a power of 10, in other words, any decimal number, can be represented with a decimal point in a fixed place. So we can move that around wherever we'd like. So we'll have a wee look at a denary example. So the kind of question you may get is represent 1.37.589 in floating point. So if we put that into the correct format, we want to get the 1 as before the decimal point. So we'll shift that over and again, and we would get 1.37589 times 10 to the 2 because we've moved it 2 places. So pulling the numbers out of here, our mantissa would be 1.37589. Our base would be 10 because we're dealing with our denary number system, so it's got 10 possible numbers from 0 to 9. And then our exponent, which is our power, is the 2. The other option that you might get is also the binary examples. So we'll have a wee look at one of those. So a binary example question could be represent 110110000 using floating point. Now again, what we want to do is we want to move our decimal point from here to the stage where we have no zeros essentially included. We want to get rid of as many as possible. So we move it 1, 2, 3, and 4. So our mantissa is going to be this value here. So we would have 11011 times 2. Now, as I've put a wee note down the bottom in terms of additional notes, the base is 2 because when we're dealing with binary, we can only have a 0 or a 1. So we have 2 options. So it's 110111 times 2, and then our power is 4. But seeing as everything else is binary, we can't just slap a 4 on in the power here. What we need to do is we need to use the previous steps from the other day of converting denary to binary numbers, and we would get an exponent of 100, which in other words is our 4, 2, 1. Nothing on the 1, nothing on the 2, so our power is 4. So we would have an exponent of 100 essentially, even though in reality that means 4. So making sure that you're familiar with all the steps that we've covered today, please go ahead and try and complete the assignment that was posted. If you have any further questions, please feel free to get in contact with me through the usual channels, Microsoft Teams, or you can email me directly again. Thank you.